Hi, I'm William Spaniel. Let's learn some game theory. Today we're going to go over backward induction. And to do that, we're going to use this game that I created precisely for this purpose. I'm calling it the backward induction game. And it doesn't really have any intuition or story behind it. I just want to use it to go over the intuition behind backward induction and how to solve games more complicated than Selton's game using backward induction. Selton's game, of course, being what we were looking at in the last two videos. So in this game, player 1 stays or goes. If he goes, player 2 leaves or joins. And if player 2 joins, then player 1 agrees or disagrees, and those are the payoffs associated with each of those outcomes. And so with backward induction, what we're going to be doing is looking forward to the end of the game and working our way backward. What do I mean by that? Well, rather than trying to explain it, I think it would be best if we went over an example here and you can see for yourself how it works in practice. So what we want to do is we want to start at the last subgame of the game. And the last subgame of this is just going to be, well, right here, when player 1 either agrees or disagrees. When player 1 makes this move here, he knows exactly where he is and how he got there. It means that player 1 originally had to go and then player 2 joined. That's how player 1 gets in this situation. And so now that player 1 knows exactly where he is and what happens when he makes each of these moves, agrees or disagrees, then player 1 can rightfully choose, well, which strategy plays the best. And that's going to be disagree here for 15 being better than 10. So player 1 would want to disagree because 15 is better than 10. And the idea of using backward induction to find subgame perfect equilibria is that your subgame perfect equilibrium will have a Nash equilibrium in every subgame of the overall game. So right here, the Nash equilibrium is going to be for player 1 to disagree for the logic that we just explained. So when we go back to this original game, instead of looking at this subgame now, where it was originally agree or disagree, we know what player 1 is going to do. He's going to disagree. So rather than having some sort of uncertainty between this payoff here, this 15-5, and this 10-10, the Nash equilibrium of this subgame is going to be 15-5. So we can just replace these two payoffs with just this one, and now we can condition player 2's behavior based off of that. So what do I mean by that? Well, if we chop off this other part of the game and we go to this subgame where now there's two things going on here, well, we know that if player 2 were to join, then player 1 would disagree. It's in player 1's best interest to do so. So if player 2 joins, she is not going to get -10. She knows that. She's going to get 5. So player 2 would not want to leave here because -5 is worse than 5. If player 2 joins, then player 1 disagrees and she ends up with 5. Now, player 2 might want to leave if she thinks that player 1 would agree here, because that would leave player 2 with -10, which is much worse than -5. But there's just no reason why player 1 would do that. So we've replaced this payoff with this Nash equilibrium payoff. And knowing that, we can now see that player 1 would not want to leave. She would want to join, and then that would cause player 1 to disagree. So now we can work back one last step, and we get to the original game as a whole, where now we've just replaced these agrees and leaves with a join disagree. So we know that if player 2 goes, that player 2, it's automatic that she's going to join and that player 1 is going to disagree, and we'll end up in this outcome. And given that, player 1's choice between staying and getting 0 and going, having player 2 join, and then player 1 after that disagreeing, well, 15 is better than 0. That's what player 1 would want to do. Player 1 might not want to go if he thought that player 2 would leave, because that would leave player 1 with -5, which is worse than 0. But that's just not going to happen. Player 2 would want to join because she knows that player 1 would disagree. So that is the outcome of this game. Player 1 goes, player 2 joins, and player 1 disagrees. And we can write the equilibrium just like this. Player 1 goes and disagrees, and player 2 joins. And that's just about it with backward induction. I think backward induction, at least the introductory, straightforward parts of it, it is one of the easiest concepts for players or for game theorists or people learning game theory. It's one of the easiest things for them to pick up on. It's very intuitive, very natural. It seems just like a very logical way of solving games. And indeed, as we saw here, I think it pretty much is exactly that. It is very straightforward and intuitive. But it can get a little bit dicey when you start adding extra information sets, simultaneous move games like a stag hunt at the end of one of these information nodes, something like that. And we'll actually be going into those particular cases in future videos, and we'll ultimately see that despite backward induction's somewhat straightforward concept and intuition, that there can actually be problems with it. But that's for future videos, and I hope you join me then. I'll see you there.